Hello and welcome again. This is a continuation of the last video on one-way functions. So you are basically just reviewing some concepts about functions, and we were in the middle of some examples of bijective functions, those that are one-to-one and onto. Now, if you don't remember what that is, I will suggest you watch the previous video on that. Alright, so I want to give you another example before we move on to the next thing. So what I'm going to do is I want to take my domain and my range or codomain to be the numbers from 1 to 10. And my function is going to be defined by this mathematical expression, which is whenever I have an input, I get 2 to that input and then to remain the modulo 11. Now this chart that is here, this table, tells me what the function actually does coming from this expression here. So for example, if x is 1, 1 goes to 2. Because it's 2 to the 1 modulo 11, which is 2. And if you look at, for example, 8, that would be 2 to the 8 modulo 11, and that 8 will give me 3. Now, just by looking at this table, I can actually realize that this is a bijective function. Thinking about this as your set A, and the second row is your set B. Of course, it's not in the same order as in here, but it doesn't matter. Then you can see here that is a one-to-one, so there are no two numbers that go into the same, and it's also onto, of course, because the same numbers here and here. Now, because this is a bijection, then there is a function that is the inverse of this one, which is the one that undoes whatever f does, which is basically this function g that I'm putting here. So just reverse the arrow. So if 10 goes to 1, then 1 will go to 10. So remember what the idea is, that g does whatever g undoes whatever f does. So that's the other example here. This is another formula. You can write it down like this, the inverse, or you can just say exactly what g does. So g to 1 is 10, g of 2 is 1, which is here, g of 2 is 1, and g of 3 is 8, which is here, g of 3 is 8, and so on. Right? So that's another example of a function that is a bijection, and we write down the inverse. Now, writing down the formula for the inverse might be hard because this formula is harder to invert in terms of something that we know. But we know that the function g actually exists. So you don't always have a formula for this in terms of a closed formula for it, in terms of elementary functions. But that function will exist anyway. All right, so why are we talking about inverse functions here? Because if you have a function here, so we know this f, function f from a to b, which is our function. The inverse function we're gonna denote it by f inverse, which goes from b to a, so it does the opposite. Like in the picture here, if f takes elements from a and transform those to b, f inverse will go backwards, right? So what do we do this kind of things? Because in cryptography, if you want to use a function for encryption, just for encryption, that function better be a bijection or at least a one-to-one function, because if it is not, then you don't. If it's not one-to-one, two plain text will go into the same ciphertext, which is not very good. So you don't want to that. So in cryptography, if you want to use a function for encryption, that function at least has to be a one-to-one. And of course, so the inverse function will be used for decryption, for decrypting the messages. So that's why we review all of these inverse functions. Now we are ready to talk about the intuitive definition of a one-way function is. So what is a one-way function? Okay, so let's look at the definition. So what is a one-way function? It is a special kind of function. So it's a function from a set A into a set B that has the following properties. F of x is easy to compute for every element x in A. And this term easy, of course, is in the intuitive sense, computationally easy. That's what I mean, computationally easy. So easy for, if they give me an input here, I can easily compute the output. It's computationally easy to do. And the second condition is probably the most important, is that for essentially all elements in the image. So if you take an element here in the image of B, it is computationally infeasible, in other words, hard, to find the x from which one they came from. So if I know that I have an output, it will be really difficult to compute where it came from. For essentially all, I will explain in a little more detail what this essentially all means. So the idea is basically this: going from A to B, giving an input and getting an output is computationally easy. The other way around is that it's the computationally hard. So if you give me an output, it's computationally hard to know from what input that output came from. And that's basically what this definition says. That's what a one-way function is. And the reason we're talking about intuitive definition, because there are some terms here that are not defined formal mathematical, but they have definitions in formal mathematics. This computationally easy, essentially all, and computationally infeasible. And this is what I just said here. So I have a function here. So I have my function, which is the function f there. So let me just erase that. That's the function f. So I can compute easily from x to f of x. That's easy. But given a y in the range of, on the image of f, it would be computationally infeasible to go back. Now, this definition does not require that the function is a bijection or a one-to-one. So finding this x, you might have many x's here, but that's okay. You don't have to be bijection to be a one-to-one function. The only requirement is that this thing here happens. So what I want to do now is talk about a little bit about the terms that I call easy there. So let me put this remark here. So there are, as I said before, there are precise definitions for easy and computationally infeasible. The reason we don't talk about that is because that's gonna distract you from the actual concept of being a one-way function. And I will probably don't tell you what this is mathematically. It's just think about it like that, and that will just be enough for the class. The second observation is this: the phrase essentially all, which is in the definition, let me read this, refers to the fact that there are values here in the image for which it is easy to find the pre-image. So basically what it means is this. Let me go back here to the definition. Essentially all means, it doesn't mean that it's computationally infeasible for all the elements in the image. Is for most of them it is. So there might be cases that you can give me something here in the output and I can easily tell you where it comes from. So essentially all basically means is what you think it means. It's just essentially for all of them is computationally infeasible to do that. But there could be some cases where I can easily find you the x that goes into y. So that's fine. All right, so what we want to do here is give you some examples of one-way functions. So let's look at some examples here of one-way functions. So let's say my inputs are 1 through 16, all the numbers from 1 through 16 are whole numbers. And my mathematical expression here for f of x would be 3 to the x, whatever the input is, and then modulo 17. So the remainder when you divide it by 17. Now let's make a table of values for f. So basically what I'm going to do is I'm going to just evaluate the function at all these points, and I'm going to get an output here. So the table, as you can see it over there, I have here my x values, which is this corresponds to the set A that I have over here. And then f of x will be just plugging in here. So for example, let's look at a particular example. Let's say 7. So 7 means f of 7 will be 11. Basically that comes from here, 7 here. So 3 to the 7th power, and then modulus 17, that gives me 11. If you go ahead and compute that, so it means 3 to the 7th power, remainder 17, that gives you remainder 11. And you can actually fill out this table actually very easy like this. So that's another way to see the function with this table. Now this is easy to compute in the sense that, for example, you can usually apply the square and multiply algorithm to make it really easy. If this were a large number, you will do that, and the answer will be very easy to compute for any single value of x. Now, if you do it the other way, so however, if compute an x for which this happens, let's say somebody tells you and you don't know the table. Let's say you don't know that table, you just know this. I'm looking, this is the output, and I'm sure that the output is 16, or maybe I wanted to find if there is really an input whose output is 16. So I have to find 16, the value of x, in such a way that 3 to the x modulo 17 is 16. If you look at what the problem is here, this is actually harder, because this is basically amounts to solving an equation, a modular equation, which is usually not easy. So this is harder without having, of course, a table. So basically what I have here is this. I have my 16 here, which is my output. I'm trying to see where that comes from, with that number x that's produces 16 here. Now, if I have the table, that of course will be very easy. So I have the table, I just have to look at 16 here. That's what my y value, it comes from 8. So x is equal to 8. So if I have the table, that would be very easy. But if I don't have the table, that would be hard. So that's what it says here, right? Now, but that's not this same for all the numbers. So for example, if you try to solve this equation, let's say here I have the number, let's say I have the number 3 here. I want to find out where that number comes from. What is the input that generates that number? So what is that number? That is actually not hard to do, because if you actually look at the equation that you have to solve, it will be this one, right? So which x gives me the 3 to the x modulo 17 gives me 3. Of course, the answer is 1. We can actually don't have to compute anything, because 3 to the first is 3, modulo 17 is 3 again. Now, we will consider this a one-way function in the sense that the values going back are hard to compute where this 16 comes from for almost all of them. You see, that's the concept of one-way function. Maybe not for all of them is difficult, but for most of them is difficult. For 16 is difficult, but not for 3. Now, I'm gonna do this remark here, because some of you might be thinking, well, this function is not really a one-way function, because finding the inverse here will be actually really easy. And the reason it's really easy is because these are more small numbers. The numbers in the previous example are small. F can be computed easily. But that's not the point of this example. The point of this example is this, that the amount of work of computing f of x, which you can do that using the square and multiply algorithm, is a lot less of the amount of work of computing x such for which y is equal to f of x. So think about this as an equation you have to solve for x. Y is given to you, that's the output is given. So you know this. You need to find what is the input whose f of x is actually that output. This is actually solving an equation. This is just a straightforward computation. So that's the idea. Now, to give you just an example of kind of like a real word, if you want to call it like that, one-way function, let's actually throw some big numbers here. So let's look at some example of a one-way function. So I'm going to take a couple of prime numbers, and I will tell you exactly what the one-way function is, but I have to do some setup first. So let's take this prime number here, which is of course it's a big number, prime number, and then you will have to believe me that this is a prime. You can actually check this with some software. And I have another prime number q that I chose also here. So this is another prime number q. I'm gonna take the product of those two prime numbers, and if you are looking at this and you actually watched the RSA, this looks very similar to the RSA, and I will tell you what the function does in a second. So the n is equal to the product of those two, and of course it gives me another huge number here. Now, what is gonna be my function? So my function is gonna act on this input, the numbers from 1 to n minus 1, when n is this big huge number here. So of course this set A is large, it contains a lot of numbers there, right? And we're gonna take this function. The function is gonna be defined on this set. It's gonna take inputs from 1 to n minus 1 when n is this big number. And for every number here, it's gonna take the cubic power and then modulo n. Alright, so this is gonna be a one-way function, because what happens here? How do you compute f of x? It is supposed to be an easy. So computationally easy. So computing this is easy for all of the numbers here. How do you compute this? If you were to do it, for example, in Java, we'll just do the square multiply algorithm. That's not very difficult to do. So if you choose a number x here, so if I choose, for example, this number, which is also kind of big, if I actually compute this in the computer, it takes this much time, 0.000021 seconds to compute. So you see, this is doesn't take too much time to do. And it gives me this answer. So that would be the f of x for that n that I show you and the x that is right here. So it gives this answer. Now, how can you do that? Actually, I did this in Mathematica. So Mathematica, maybe you know about this software. It's related with Wolfram Alpha a little bit. And I essentially did it here in Mathematica because it's a little bit easier than doing it in Java. It has all the functions that I need. So just to save some time. So in Mathematica 11, which is the current version, you will type this timing, which is basically going to tell me how much time the computation is going to spend. That's how I got this number right here. How much the computation is going to spend. And power mode is what you think is going to do. Power mode takes the base is this here, which is my x. This is the exponent, and this is the modulo. So this does modular exponentiation in Mathematica, which is nice. It's just a command that you just type it like this with brackets here. And this timing here, closing this bracket, is going to tell me the answer together with how much in seconds that took. So that's how I got this number right here. Okay. All right. So now the other way around is that was easy to compute. The other way around will be something like this. I want to find x for which x cubed modulo n is this number. So this is another complete different number. I want to inverse the function. Means I want to find the input x for which the output is exactly this. This amounts to solve this equation here. Okay. So let's try to do that. Now, I'm saying this is a hard problem. So this is a one-way function. This is to compute what the output is, but given the output is hard or computationally infeasible to compute the input. So let's say we ask Mathematica, which is powerful software. It's not the best in number theory, but it's not the worst either. So in Mathematica, you will do something like this. You will try to solve this equation here. My variable, I'm going to change it for y. So I want to solve y cubed equals to the y value, which is, this is the y value that I have. This is given to you. The variable here is z, and then this equation is modulo n. So it's an equation, a modular equation. So basically, this is the command that solves modular equations. You put the equation here you want to solve, and then that should be a double equal there. And then this will give you the solution together with the time that it takes for this to give you the answer. Now, I can tell you this, and I'm going to show you this in Mathematica. I type all this in Mathematica, and it took more than 4 hours, and I didn't get an answer from this. So basically, what this is saying is really easy to compute the function here. Look at how little it took, but it was very hard for Mathematica. Mathematica didn't even found the answer in 4 hours doing this. So trying to find the x for which this was the output. So I will go to Mathematica and I will show you how I did that and exactly why it took 4 hours. So I'm here in Mathematica, and as you can see here, I have a couple of things that I want to define. So the first one is the number p here, the variable p that I was showing you in the video. So I just go there and I define my variable p. It just tells me that that's the value of p. Then I'm gonna do the same here for q, and so I'm basically just defining p and q. And now I have n, which is the product of the two primes p and q, and that's exactly what I get. Now that x value that I have there is what I had in the video too, so basically just doing the same I was doing before. And that's the line of code that I was using to compute the power mode of the modular exponentiation. As you can see, the number there 0.00021 was what I had there before. The variable y is also what I had in the video. And now I'm trying to compute the input from where that output y came from. So just look at the attention here at the time there. So it's 6:47 p.m. So I'm gonna actually go ahead and hit enter and tell Mathematica that go ahead and compute that variable z there, which is the solution of that. So to get the answers, I just hit enter there, and so Mathematica starts doing the computation. As you can see up there, it says running, and again, look at the time there, and later I'm gonna show you about 4 hours later, that's gonna be the answer. So I'm here back in Mathematica, and take a look at the time again. The time is 10:49 p.m. Mathematica is still running and it hasn't been able to find the answer yet. So it's about a little bit over 4 hours. And of course, I'm not gonna sit down here and wait for Mathematica to do this. My guess is this is gonna maybe take days, or maybe Mathematica won't be able to give us an answer. That's just show you exactly how hard it is for these expressions or these things to be solved. So the point of this whole thing in Mathematica was to show you that one way was very easy to do, even now with the computers that we have today. So it's very easy, just a square multiply algorithm. But the way going back is really hard, even for a Mathematica, which is a pretty good software. So I'm gonna stop the video here, and in the next video I'm gonna talk a little bit more about one-way functions and some of the things that we haven't discussed yet. So I will see you in the next video.